Great.
Right. Good morning, everybody. We are here to see what Kade's been working on the last 2 years. And Kade came to us from College Station, and as he reminded me this morning, it was almost 2 years ago to the week. So he came in and he started working on a project that Ryan Felton had been working on for a couple of years in developing a new platform for sampling waters and agricultural streams. Ryan's work was really important in figuring out how to make that work from a logistical standpoint. And it's been really fun to watch Kade work on this because he has taken that platform and really put his brain on it in terms of trying to figure out what can we learn from these new flavors of data that we didn't already know previously. And I'm not going to steal his thunder. There's a lot of really exciting stuff in here, so I'll turn it over to Kade. And yeah, I think that's it. So go ahead, Kade. Oh, and also I'll be moderating the Zoom. If you have questions, just go ahead and put them in the chat. We'll probably save them until the end.
Okay, thanks for the introduction, Brent. Thanks to everybody here on the room and on the Zoom, especially my family. It's really nice to have you here. So the title of my thesis, Nutrient Loss from Agricultural Landscapes, Perspective from the Stream. Before talking about this perspective of which we're looking at nutrient loss, I want to talk about kind of the broad motivation for this work, which took place within agricultural watersheds in the Midwest. So the Midwestern United States contributed 47% of the market value of agricultural products sold in 2017. And between 2010 and 2014, the US made up over 13% of world exports. So agricultural productivity from this region really is of global importance. And there are a few modifications that have really enabled that. One is the use of synthetic nitrogen fertilizers. You can see in this map from Cal et al. That through time, the use of fertilizers in the United States has increased, and much of this use is concentrated within the Midwest. Another modification to the landscape is the installation of subsurface tile lines to lower the water table in these agricultural fields in order to support crop production. So this map from Frankenberger et al. Shows an estimated extent of agricultural drainage within the Midwestern states. And so you can see this is prevalent throughout the region. So that begs the question, why measure in these headwater agricultural streams? Well, this combination of adding nitrogen to the landscape, draining water from the landscape to these surface water streams, as well as human-induced climate variability that's increasing precipitation in the region, has kind of created these conditions in which a lot of nutrients are lost from the landscape. And there are environmental consequences of this. Pictured in the background of the slide is the extent of the Gulf of Mexico hypoxic zone in 2022. This is kind of a continental scale issue that is largely attributed to nutrient loss from these Midwestern states. This environmental degradation is also notable within the state of Minnesota. So this map of the state shows rivers, streams, and lakes that were designated as impaired by the Minnesota Pollution Control Agency in 2022 due to nutrients or nitrate. So we have this continental scale environmental degradation, this local environmental degradation, and any loss of nutrients from the land surface is a direct economic loss for the farmers because they're paying to have these nutrients put on their field in order to support crop production. And then, of course, there's indirect economic loss due to this environmental degradation. One way to address the issue of nutrient loss is to implement conservation practices on these agricultural lands. So these can be, field practices such as cover cropping, which have been shown to reduce nitrate leaching, edge of field practices like the installation of buffer strips to reduce sediment and phosphorus loss from stream banks, or downstream practices, including the installation of wetlands to intercept these nutrient-rich waters before they're exported further downstream to these more environmentally sensitive areas. In this map in the bottom of the slide, is an output from a geospatial tool called the Agricultural Conservation Planning Framework, or ACPF. And this is a tool that uses geospatial information to prescribe potential sites that conservation practices could be implemented. So I want you to notice here is that each of these conservation practices are recommended at a specific location in space. So the solution is very local. If you contrast this with the way that nutrient loss is typically monitored in these agricultural watersheds, that spatial scale is much larger. So most commonly, you'll have sensors installed near a watershed outlet, and you'll be tracking movement of water and movement of nutrients continuously. But if you implement one of these, recommended conservation practices, evaluating, potential positive outcomes from that is really difficult because your signal from that conservation practice might be really hard to detect when you're monitoring this much larger drainage area. And this is kind of the motivation for this packraft. As Brent mentioned, it's a tool for flow path sampling. The principle here is that by paddling this packraft within these headwater agricultural streams and measuring nutrient concentrations and other water quality parameters at this high spatial resolution, we can then connect those measurements to management practices on the surrounding landscape in order to evaluate the effect that what happens on the landscape has on what happens in the stream. The sampling platform can sample in low order streams where catchment area is small, and so you have a greater chance of having enough signal to really detect these potential improvements from field scale practices. And with repeated sampling, you can capture temporal changes in much the same way that you do if you're monitoring continuously at the watershed outlet. So a little bit more on the specifics of the sampling platform. The entire platform is based on, the brand is packraft, but it's an inflatable packraft. And what's unique about this over a traditional kayak or canoe is that it has a very low draft. So we're able to sample when water is quite shallow during low flow conditions, and also these smaller order streams. On the exterior of this packraft, there are spectrophotometers and other sensors that are measuring directly within the water profile of the stream. And these sensors are logging on internal data loggers stored in this cooler, which also houses a GPS unit. So each time these sensors take a measurement within these streams, it's logged on the data logger, and we have a coordinate showing the location at which that measurement was taken. This occurs at a pretty high temporal frequency, so we have a measurement, every 10 to 50 meters within these streams. We also have a system called this Bandolero discrete sampler, which allows for water samples to be semi-automatically collected so that these samples can be taken back to the lab and analyzed for parameters that our sensors don't measure, or to validate these sensor measurements. And this bottom panel just kind of shows the capability of the sampling platform to really navigate up to these features of interest like tile outlets and to potentially sample them directly. But all the data I'll be presenting today kind of focuses on measurements from within the stream channel. This figure from a paper in review, the lead author, Ryan Felton, the master's student that preceded me, just kind of gives you an idea of what this data looks like. So in the bottom panels, you see two maps from two different sampling events. This gradation in color shows the change in nitrate concentration along the stream reach that we paddled. And you see, labeled on here are tile outlets as well as a wetland here. And so at these features, we see changes in the stream water chemistry profile. These two-dimensional plots above the maps show the exact same data, but just a little bit differently. So on the x-axis, you see channel distance to the watershed outlet. So this is like a measurement of the stream location. And on the y-axis, nitrate concentration. So again, you see sensitivity to these small features such as tile outlets, and then kind of larger changes at the location of these wetlands. Throughout the remainder of my presentation, I'm going to be presenting the data mostly in this two-dimensional plot format. But when you see this, kind of just remember that these are kind of measurements taken in space, influenced by a surrounding landscape. This plot just communicates kind of the sensitivity to small changes in nitrate concentration that we can detect with our sensors deployed from this packraft. So again, we see nitrate concentration on the y-axis, distance to the watershed outlet on the x-axis, and the black dots are packraft sensor measurements, and these red dots are grab samples that were collected and then taken back to the lab and analyzed. You see some offset between the packraft sensor and the grab samples, but what we're interested in is really the relative change here. So from the start to the end, the change in nitrate concentration between our grab samples and our sensor measurements is nearly identical, which gives us confidence that, in this sort of deployment configuration, we can pick up changes on the order of like 1/10 of a milligram per liter, which is in line with the manufacturer's stated performance of these sensors. And so, previous work has kind of established that this platform enables us to collect this high resolution stream water chemistry in these headwater agricultural streams. So my efforts really focused on understanding what the utility of measuring stream water quality at this high spatial resolution in headwater agricultural streams is. Why might a researcher or manager be interested in collecting this sort of data, and how can it be used to guide management in order to address some of these issues facing society? And I look at this in two ways. First, by integrating the packraft sampling data with traditional fixed point monitoring of nitrate and discharge. And then secondly, by linking the landscape and stream water quality at these small spatial scales. So getting into the first chapter, looking at stream nitrogen dynamics from multiple reference frames, including this fixed point monitoring. Kind of in the background of this slide, you see two images taken at the same location. On the left-hand panel, this is in our study watershed this spring, and then this right-hand panel is the same location during the summer of 2021. So I think these images just really communicates the temporal variability that you can see in these headwater agricultural streams. And so by monitoring even at a single location in space, we can really capture a lot of, how these stream nitrate dynamics change through time. So I'll talk a little bit more about the area that we were studying in. The watershed we worked in was High Island Creek watershed, which you see here is a tributary of the Minnesota River, which flows into the Mississippi River. So it's directly, export from this watershed in particular is directly connected to these local and continental scale environmental issues that I talked about in the introduction. And the entire watershed really is dominated by cultivated cropland, which is shown here in brown. One thing I'll point out is that in the upper reaches of the watershed, there's this lower density of lakes and wetlands compared to the middle reaches here. And later on in the talk, the influence of this large lake, High Island Lake, will become kind of important. So even though agriculture is dominant throughout this watershed, we do see this gradient or this variability in the amount of nitrogen applied to the landscape. So this map shows an estimate of nitrogen input based on crop rotation history and recommended fertilizer rates, locally relevant to this area. And we see that within the upper reaches of the watershed, typically more nitrogen is used compared to these lower reaches of the watershed. We also see this gradient in the percentage of lakes and wetlands. So less lakes and wetlands within the upper reaches of the watershed, more drainage. There's a lot more tile lines that terminate directly into the stream, as well as a lot more of these very notable artificial ditches compared to the middle reaches of the watershed, which, like I said, have these higher percentage of lakes and wetlands. And we have these two fixed point monitoring stations, one lower down in the watershed, site 1, our downstream gauge, and one further up in the watershed, site 2. And if we look at hydrographs from these two locations for the study year, 2022, first we'll note that during 2022, discharge decreased throughout the summer until the stream dried up in early September. And for this year and the year preceding it, water yield was less than 40% of the 10-year average. So this study really was conducted during some severe drought within this watershed. Just to describe this figure a little bit more, this is showing discharge through time, what we call a hydrograph. And if we compare the hydrograph from that site 1, the downstream gauge, to the site 2, the upstream gauge, we see very different hydrology. So at the upstream gauge, we see a steeper rising and falling limb, peak discharge that is higher, and this really is a reflection of the drainage intensity. So like I mentioned, water is being pushed from the landscape more in the upper reaches of the watershed and stored, and this peak discharge is buffered as we move down into the watershed. So kind of shifting focus and really talking about this fixed site monitoring of concentration and discharge relationships. We looked at this on 2 temporal scales. So first, we considered seasonal concentration discharge relationships, and then we looked at the concentration discharge relationships of individual storm events. So to look at these seasonal dynamics, we used 2 metrics. One is a parameterization of the discharge and concentration plot using this power law function. So if you plot concentration and discharge in log space, you can fit a line, and that slope can be used to classify the export characteristics of the watershed. We see, some theoretical examples of this in this figure on the right. If concentration is increasing with discharge, we have these chemodynamic and enriching behaviors. If the slope is negative, concentration is decreasing with discharge, and we have these chemodynamic and diluting behaviors. And if the slope is near 0, we have these kind of constant conditions where concentration is not varying much with discharge. Another way to consider this is by comparing the coefficient of variation in concentration relative to the coefficient of variation in discharge. We can use both these metrics together to classify the export characteristics of the watershed. This figure, adapted from a paper that sort of established this dual approach, shows how we can use the CVC, CVQ to differentiate between these chemodynamic and chemostatic conditions, and then the slope of this function to describe chemodynamic conditions as either mobilizing, where concentration is increasing with discharge, or diluting, where concentration is decreasing with discharge. So this is how we can evaluate the concentration-discharge relationships across seasons. Now to look at how we can evaluate these relationships of individual storm events, where we're considering just the rising limb and falling limb of a hydrograph. In this upper panel, we see a situation where you have a hydrograph and chemograph, so a measurement of discharge through time and concentration through time that perfectly align. And in this situation, you'd have this straight line behavior in this concentration discharge plot. More often, though, you have this effect of hysteresis, where the peaks in concentration and discharge differ. And in these concentration discharge plots, you might get these loops that form. For example, a counterclockwise loop when concentration peaks after discharge, or these more complex patterns due to different skewness of the concentration discharge profiles. And we use these to help us interpret the solute export behavior from the watershed on this kind of short event timescale. So to look at data from High Island Creek at our most downstream locations, we will look at concentration and discharge relationships, daily values, broken up by season, and these different flow regimes. So based on our classification, we see that for summer base flow, summer storm flow, spring base flow, and spring storm flow, we had chemodynamic conditions across the board. And you can visualize this in this plot of concentration and discharge on the right. So here in the summer, in agricultural watersheds, this chemodynamic behavior is often attributed to in-stream processes such as biologic uptake or denitrification, which are more active when discharge is lower and residence times are higher. In the spring, we also see this chemodynamic behavior, but in agricultural watersheds, especially at these higher levels of discharge, this behavior is more often trending towards chemostatic. And furthermore, in these high flow, cold temperature conditions, we wouldn't really expect that there's a lot of uptake or denitrification happening within the spring. And so even though we have similar export patterns, the processes influencing these these export behavior differ between the seasons and flow regimes. And looking at just this summer base flow, we have an indication that there's denitrification happening within the stream, but this isn't a direct measurement of where that's happening or to what extent. So because this behavior was a little bit unexpected, we compared for a subset of dates these same relationships between our downstream and our upstream gauge. So looking at the concentration discharge relationships across space. And here we see for this subset of dates at this downstream location, we still have these chemodynamic conditions, chemodynamic and enriching. But at our upstream location, this export pattern is classified as chemostatic. So this is an indication that there's difference in nitrate source zones between upstream and downstream of Site 2. Like I've mentioned, one of these big differences on the landscape is the proportion of lakes and wetlands between these two sites. Of particular interest is the outlet of High Island Lake, which is connected to the stream via this non-controlled outlet. So when the stream water is high, it flows into the lake. When the stream water is lower, the lake flows into the stream. And this large lake represents, this low solute source zone. So it's probable that this kind of change in the direction of the flow, the change in how the lake is contributing to the stream, is influencing this chemodynamic behavior that we observe downstream of the lake, but not in these headwater catchments. But, with this sort of analysis, we're not necessarily measuring the influence of these individual features specifically. So looking at storm events, one of the hysteresis patterns that emerged was this counterclockwise hysteresis, where when we're tracking concentration and discharge, we have this peak in concentration after this peak in discharge, which again forms this counterclockwise loop. So concentrations are higher on the falling limb than they are on the rising limb. And so this indicates that there's this lagged response of nitrate mobilization. And one thing that could describe this is a distal source of nitrate. So at the onset of a storm event, nitrate moves from the landscape into the stream, but because this happens further upstream, we don't observe that until much later in the storm event when we're monitoring further downstream. And in Highland Creek, I showed we have this overall greater nitrogen application in the headwaters compared to further downstream. So, this fixed site monitoring, which is not really the focus of this study with this packraft sampling, is still cutting edge because these optical sensors to monitor nitrate are relatively new. And these data reveal that there are spatial controls on solute export, such as this distal source or this difference between these two locations. But with this approach, we're not uncovering the specific spatial controls. We're not sampling the influence of these features individually. So that's where we now apply our packraft data to help us aid in interpreting these behaviors that we observed by monitoring at just a couple locations in the watershed. And we do this by looking at, by comparing the stream water chemistry profiles between different sampling events taken through time. And one way we can quantify this is by looking at the spatial stability, which is just a measurement of the similarity between a single sampling event and the average conditions along that stream reach. So just to demonstrate this, if we have here a plot of stream distance to the watershed outlet on the x-axis and concentration on the y-axis, so this represents a stream reach. And we paddle this on two different events. If this pattern in nitrate concentration that we observe is similar, this would be classified as a region with high spatial stability. Conversely, if between these two events, this pattern in nitrate concentration is variable, this would be low spatial stability. This indicates that the features influencing the stream nitrate concentrations that we're measuring change through time. We look at this metric spatial stability along three characteristic stream reaches throughout the watershed. So this eastern stream reach is characterized by flow through lakes and wetlands, so lakes and wetlands that the stream moves through that we paddled through, as well as these smaller riparian features. This lake stream reach is characterized by the outlet of High Island Lake. And then we have this western stream reach, which is characterized by conditions within the upper portions of the watershed. And we see that spatial stability was lowest for this east stream reach and highest for this western stream reach. So remember, this eastern stream reach is characterized by these two flow-through lakes and wetlands here, as well as these riparian lakes and wetlands that are connected to the stream via these ditch outlets that are marked with these red diamonds. So this stream reach, we started here and paddled downstream. This low spatial stability is an indication that the influence of these features is variable through time. And the real strength of this sort of packraft data is that we can visualize that variable influence through time. So for that same stream reach, this is that plot of distance to the watershed outlet on the x-axis, nitrate concentration on the y-axis, with the location of these wetland and lake outlets draining into the stream marked, as well as the location of these two flow-through lakes. And we see during this high flow event early in the spring, nitrate concentration decreased drastically at the location of these lake and wetland outlets, and actually increased at the location of these flow-through lakes. If we contrast this with the sampling event much later in the season and at much lower levels of discharge, we now see that there's no drastic decrease in nitrate concentration at the location of these ditch confluences. And now we do see this decrease in nitrate concentration at the location of these flow-through lakes. So this is indicating that during these low flow conditions, hydrologic connectivity of these riparian features decreases. So they're no longer diluting what we see in the stream. And these flow-through lakes, when residence times are higher and temperatures are warmer, are sites of increased nitrogen transformation. So looking at spatial stability along this lake stream reach, which again is characterized by the outlet of High Island Lake, which is bidirectional, we see during this high flow event, as we paddle past it, there's no change in the nitrate concentration in the stream. During this low flow event, we see this drastic decrease in nitrate concentration. This is when the lake is contributing to the stream. And this decrease is of a large magnitude. It's nearly 6 times higher than that decrease along the eastern stream reach on this same date. And so not only is this lake having a variable influence on our measurements of nitrate concentration, but the influence is also quite high. And then looking at the western stream reach, where we have this high spatial stability, we can compare these stream water chemistry profiles for a high flow event and a low flow event. And here, we see these increases at the location of these ditch outlets draining agricultural land. And we see this same pattern between these two events. I'll just go back and forth between them really quick. The magnitude of increase changes, but the pattern is the same. So what's the benefit of looking at data in this way? Well, with this repeated sampling, we kind of gain similar information as this fixed site monitoring. We saw that there is higher spatial stability in regions with chemostatic export behavior, where landscape influences on the stream are not variable through time, and this lower spatial stability in regions with chemodynamic export behavior, where the landscape influences on the stream are variable through time. The added benefit of this sort of sampling approach is that we can disentangle the influence of individual watershed features. So we can look at the comparative effect of different subcatchments, as well as features like these different flow-through lakes and riparian lakes and wetlands. This added information can really inform on how future monitoring can be more effective by revealing new questions about watershed processes. For instance, if we can identify regions where temporally the conditions are more variable, more intensive monitoring at those sites might yield more insights. And so we can kind of use our resources more effectively in that way. And in the same way, this sort of type of monitoring can guide placement of fixed site monitoring in watersheds that are unmonitored by, again, identifying regions where variability through time is higher. And so that's how we can kind of use this packraft sampling data in the context of our fixed site monitoring. Now I'll transition into the second chapter of my thesis, which is looking at these small scale connections between the landscape and stream water quality. And we'll focus only on the very upper reaches of the watershed for this analysis. And we're going to consider two landscape variables. One is this nitrogen intensity, or this estimate of nitrogen input, which again is based on a crop rotation history and fertilizer guidelines. And if we look at a map of field boundaries for this upper portion of the watershed, we see even though it's all cultivated cropland, there is variability in the amount of nitrogen applied, which is really driven by the amount of corn that's grown on the landscape. So these regions with higher nitrogen input tend to have consecutive years of corn, which requires more nitrogen relative to these fields that alternate between corn and soybean more often. We also looked at this metric depression intensity, or the proportion of land area classified as a depression or internally drained feature of the landscape. And in this map, we see in these upper reaches of the watershed, these depressions are kind of everywhere, but there is some variability, and you can really notice that if you look at only these larger depressions shown in light gray. So at the very headwater regions, there's more of these larger depressional features, and these are areas that pre-settlement really didn't have any of this stream network. So that explains, they're much younger landscapes compared to further downstream. Many of these depressional features, like all of this landscape, are artificially drained, but they're still generally sites with higher organic carbon contents and moisture content. So if we go into the field after a storm event, these are the locations where you'll see pooling. Even when they're drained, that water is sometimes retained for multiple days. Because of these sites are potential locations of increased nitrate transformation, where higher moisture contents and carbon contents might promote denitrification, or because they're often drained, sites of increased translocation, so movement of nitrate from the land surface into these streams. So we have these landscape attributes, but how do we represent what's happening on the landscape at these stream measurement locations? So I'll illustrate this using this cartoon of a watershed. So at these different points within the stream, we have different catchment areas. And because there's variability in these landscape attributes throughout the watershed, the average conditions within each of these subcatchments, these colors, will change. For instance, if this green polygon has this really high nitrogen input, but this blue polygon has a lower nitrogen input, you'll see, a difference in the characteristics of this upstream drainage area at these different stream measurement locations. And we can visualize this in the same way that we visualize our in-stream measurements by plotting these catchment attributes on a two-dimensional figure of distance to the watershed outlet. And so by plotting these catchment attributes together with our in-stream measurements, we can kind of visualize how these different data sets might covary. So looking at these catchment characteristics along this western stream segment, this figure, again, distance to the watershed outlet, is shown on the x-axis, and this normalized intensity value is shown on the y-axis. So for depression intensity and nitrogen intensity, the maximum and minimum have just been rescaled between 0 and 1 so that we can visualize them together. When looking at this, you see that most of these changes occur at the location of ditch outlets, which makes sense because these are locations where your catchment area is changing because you have this, this ditch coming in that drains this different area. However, you also see variability along stream segments not characterized by these ditch inlets. If we rescale these land attribute values here and plot them with the location of these tile drain outlets, we see that changes are also occurring at these locations, at a much smaller magnitude. But, for some of these tile drain outlets, we have this change in the characteristics of the landscape draining to these stream measurement points. Some of these tile outlets, we see more variability, either because they're draining larger catchments or areas that are more distinct from the surrounding landscape. If we look at now a plot of these landscape attributes and stream nitrate concentration together, again, rescaled from 0 to 1 and plotted with the distance to the watershed outlet. And these circles show nitrate concentration that we measured on May 12th, a high flow event in the upper portions of this watershed. And then the blue line, the green line shows depression intensity, and the red line shows nitrogen intensity. So here we see, just like at the location of these ditch confluences where we saw these changes in these landscape attributes, these are locations where we see most of the change in our in-stream nitrate concentration. So at this first ditch confluence, we see an increase in nitrate concentration and a decrease in depressional areas. At the second ditch confluence, we again see an increase in nitrate concentration and a decrease in depressional areas. So there's this negative correlation between the amount of these internally drained features on the landscape and stream nitrate concentrations, an indication that these are potentially sites of increased transformation, of denitrification. When we look at the nitrogen intensity, we see that there's kind of this variable influence. So at this first ditch confluence, we have this increase in nitrogen intensity and this increase in stream nitrate. But at the second ditch confluence, we have this increase in nitrate concentration, but an increase in the nitrogen intensity, the nitrogen on the landscape, which doesn't really fit our understanding of that relationship. Similarly to how we can observe changes at other locations, we also see our in-stream measurements have variability as well. So if we were to rescale this section of the plot, just to highlight this variation, we see at the location of this tile outlet pictured here, it's kind of dark in the room, but you can probably see it better on Zoom. You can really see the influence that the tile has within the stream flow path. This tile drain outlet is marked with this particular gray vertical line right here. And at this location, we see this decrease in nitrate concentration and this decrease in nitrogen intensity. So the nitrate concentration decreased by about 1/10 milligram per liter at this location. And the catchment draining to this tile outlet had a nitrogen input of 20 pounds per acre lower than the average conditions upstream of that tile outlet. So here we're seeing that even at this small spatial scale, this packraft sampling platform is sensitive to in-stream changes influenced by these much smaller drainage areas. So we can get a lot of information by looking at this qualitative comparison, but there might be some interest in quantifying this landscape stream relationship as well. So we'll do this in two ways. One, by applying regression-based statistical models that assume independence between sampling points, and then two, by applying models that account for spatial autocorrelation. And that's important because spatial autocorrelation is really prevalent in these stream networks. So when you take a measurement at 2 points in a stream, because there's this water flow path, there's going to be a relationship between these two locations. It's a similar phenomenon that's seen in other environments, like soil. And there's this special class of models developed to account for the unique spatial relationships that exist within stream networks. This figure from Peterson and Verhoef shows those different spatial relationships. So you have 2 points related by Euclidean distance crossing this network. This is the spatial relationship in other environments like soil that you would use. But in stream networks, you also have relationships that are confined to the stream flow network itself. Those can be flow unconnected, and they can be flow connected, where one point flows into another, but it's really confined to the stream flow path. And as a part of applying these geostatistical models, you can use this graphical tool of the semi-variogram to explore these spatial relationships a little more. This figure from McGuire et al. Shows a theoretical distribution of a stream water chemistry within a network and a corresponding semi-variogram, which is a measurement of dissimilarity increasing on the y-axis and distance between sampling points on the x-axis. And the parameter that we'll use to kind of explore the spatial relationship here is the range, which defines the distance between these sampling points at which the spatial correlation goes away. So at this value of the range, two measurement points can be considered independent. If we look for May 12th, that same data set where we did kind of this qualitative comparison between landscape attributes and in-stream measurements, we see this value of the range where measurements become spatially independent is reached at relatively short distances within the stream. And so this is kind of an indication that with this sort of sampling strategy, we really are gaining unique information. So if you were to conduct a traditional synoptic sampling campaign where you go down to the stream bank at road crossings and collect water samples, you might be limited in the amount of information you capture because there is kind of variability at this small spatial scale within these systems. So that's a little bit of an aside back to quantifying this relationship between our two landscape attributes, nitrogen intensity and depression intensity, and our measurements of stream nitrate concentration. So first, we will assume independence among measurement points and apply this generalized linear model or this non-spatial model, then account for spatial autocorrelation using the spatial stream network model. Common in this approach of employing these spatial stream network models within these systems is to first kind of create a model by selecting fixed effect variables, comparing different non-spatial models, and then work to understand the benefit of accounting for this spatial autocorrelation. So looking at variable selection with this non-spatial model, first, I want to note that each of these models, including distance to the watershed outlet, is a fixed effect to remove this kind of large-scale gradient, which is important for employing these techniques. And flow accumulation, which I'm not showing in this table, which is the catchment area, alone accounted for large variability in stream nitrate concentration within the system. But our depression intensity had the lowest Akakis information criteria, highest coefficient of determination, both metrics used to kind of evaluate model performance, indicating that this variable accounted for most of the variability. This table is showing just the sign of these parameter estimates, so the relationship between stream nitrate concentration and these landscape variables across these three sampling dates, which were conducted within the western section of the watershed, this upstream portion, but along slightly different stream reaches. One thing to note is that while the relationship with depression intensity is consistent, the relationship with nitrogen intensity is not consistent. One factor driving this may be that the range in nitrogen intensity on this date where we saw this unexpected negative relationship was much lower compared to these other two dates. So it's quite possible that the reason on May 12th that we see a negative relationship between nitrogen input and nitrate concentration is that we're really only we're measuring in a system that does along a stream reach that really doesn't have that much variability. Talk about that a little bit more later. So now with our depression intensity model, we can compare the performance of our non-spatial model and spatial model to kind of determine the importance of accounting for the spatial autocorrelation when analyzing these data in this sort of framework. And this table is looking at one way we can do that, which is showing how the amount of variation in nitrate concentration accounted for by different parameters of that model. So we have our predictor variables, distance to the watershed outlet and depression intensity, this spatial term, so the spatial relationship between points, and then this unexplained variance or random error. And we see for the spatial stream network model, overall, the unexplained variance decreased, but also the amount of variation explained by the predictor variables decreased. And this is because we now have this spatial term. This is kind of common when comparing these sort of models that have been applied to larger branching stream networks. And in this case, it doesn't really change our interpretation of the data. In fact, this qualitative versus quantitative comparison, we kind of gain similar insights within this system. I think this quantitative approach is likely more important in systems that are more heterogeneous, where you have this, greater amount of variables influencing nitrate concentration, and not just these simple relationships of which most of the variability is accounted for just by catchment area, and you slightly improve your understanding, the amount of variability captured by including one or two of these catchment attributes. We can visually compare these two models using a leave one out cross-validation. Leave one out cross-validation is simply a test of model performance. So you have your model and you retain a single data point. You run your model and your model predicts that data point. And you can compare your measured and unmeasured value. So it's just retaining one value, predicting it, and doing that over and over and over again for every single data point within your data set. This figure shows our measured nitrate concentration in red, the estimated nitrate concentration with the non-spatial model as in green, and the estimated nitrate concentration with the spatial model in blue. And what we can observe here is that even with our non-spatial model, we capture most of these large changes in nitrate concentration, but it's these small fluctuations within nitrate that are captured by this spatial component of the model, which makes sense when we understand that even with this non-spatial model, a very large proportion of the variability was accounted for. And so, in summary, we looked at these two different landscape variables, and we can gain some insight into possible mechanisms influencing this landscape stream relationship. For nitrogen intensity, we saw this relationship was variable. As I stated earlier, this could be because there's small signal due to low variability throughout this landscape. Also, we're estimating these nitrogen inputs based on crop rotation histories. And so these aren't really reflective of actual on-farm decisions that are being made. And so it could be that a subset of fields that don't kind of follow these recommended fertilizer rates might be influencing this relationship disproportionately. For depression intensity, we saw across sampling dates and locations this negative correlation with stream nitrate concentration. Again, an indication of increased transformation happening on the landscape. Recent literature that studied these depressional features individually has kind of cited them as more often sites of increased leaching, because in these agricultural systems, they're often drained. And so it could be that there are a subset of these depressional features in our analysis that were unfarmed, or which, drainage was not efficient. And so at these sites, there was, this promotion of denitrification. So, in these two comparisons, we've shown that these data provide a new way to understand agricultural landscapes. Paired with traditional fixed point monitoring, we can gain new spatially rich understandings of watershed processes, such as the influence of individual features like lakes and wetlands. And then with pairing these data with land use information, we can evaluate the relative impacts of management practices and landscape characteristics on water quality at this small spatial scale. So with that, I'd like to say a thanks and show my appreciation to my advisors and committee members, John Baker, Brent Dalzell, and Diana Carwin, To the field and laboratory assistants that I got throughout this project: Bill Brider, Madeline Conowall, Ryan Felton, Forrest Goodman, and Todd Schumacher. Project assistance from Ryan Felton, the master's student that preceded me. He really, we spent a lot of drives out to the field site discussing this project. So a lot of these ideas came from those conversations. Joel Nelson and Sarah Porter were really helpful with a lot of the GIS components of this study. Sarah Porter, especially with the integration of these land attribute data sets obtained through ACPF. Our funding sources, the USDA Farm Service Agency, as well as additional support from USDA ARS. And lastly, to my friends and family, especially my wife, Marla. So with that, I'll open the floor to any questions. Thank you. John.
You focused a lot on a few specific semi-variograms, is what you call them, right?
Uh-huh.
And provided a lot of context to those specific dates, right? But you also towards the end mentioned that sometimes those relationships aren't the same between dates, but so I guess I'm just wondering, like, that temporal component, and how much do you learn from additional deployments of this graph on the same screen? Like, is it beneficial to lots of deployments, or would it be beneficial to cover lots of watershed?
Can you say that back for people on Zoom?
Yes. So in summary, the question was asking how best to utilize this approach, whether to, repeated sampling of short segments or one-time sampling of a larger spatial extent. Is that pretty much right? Yeah, great question. And that's something we thought about a lot. I think it really depends on your objective. So initially, with this project, we kind of had these two regions in High Island Creek. Well, I won't flip back through all the slides, but kind of this upstream region and this downstream region. And our approach was to go out, weekly to biweekly and kind of alternate between sampling these different sections. And, once I delved into the analysis, I found that in some cases, just focusing on a single stream reach and sampling it, repeatedly through time would have made some of this analysis a little bit more straightforward. For instance, like that downstream section where there's this variable influence of these lakes and wetlands. But then for other regions of the watershed, I showed that there's not much variation in this pattern of nitrate concentration. So if you were just to go out and measure during one sampling event, you would be able to capture a lot of that variability, particularly if it was an event with very high discharge, because during those conditions, we typically saw more fluctuations in nitrate concentration within the stream. And so evaluating the effect of these small features like tile drains became a little bit easier because they had a greater influence on kind of these flow path measurements within the stream. So in summary, I think it really depends on your objective. I think there's multiple ways to use the sampling platform. I hope that non-answer answered your question.
Is there any way to relate this to load at all?
Yeah.
Probably thought about that.
I think like 2 years ago, when I came onto the project, a lot of the efforts were focused on, how can we measure discharge continuously so that we can have these continuous measurements of load. And in the end, I think we just decided, like, we're technologically limited. We just really don't have a way to collect that sort of data. I think, you could go out and we attempted to do this and sample short stream segments, and where you're able to access the stream, take discharge measurements. So you can kind of have these blocks of stream, and you can look at changes in nitrate concentration along them. And then if you bookend them with discharge measurements, you can kind of understand if these changes are due to dilution or mobilization, or if your discharge at these two endpoints doesn't change and you have a decrease in nitrate concentration, that's likely due to in-stream processing. And so there are ways to do it, but not sort of seamlessly and at the same spatial resolution that we're tracking nitrate concentrations.
You have data though that show that instantaneous water yields expressed to depth equivalents.
Yeah.
Pretty homogeneous,
Yeah.
right? So
Yeah. So you could turn that into load, but this would probably, only work for some locations. So the regions where there's a lot of these flow through lakes and wetlands and probably more, groundwater dynamics, this relationship that we established probably wouldn't hold. But in the upstream reaches of the watershed, yeah, like Brent mentioned, we observed that, measuring water depth, gives you a pretty good estimate of discharge. So.
say something about private property.
Right. And, logistically, it's difficult to measure discharge within these headwater agricultural streams because you kind of have to be stomping around on a stream bank. When we're measuring these nitrate concentrations, we're within the flow path of the stream, so we're not trespassing on these adjacent agricultural properties. And so that's why you're sort of limited to measuring discharge at a few points because, at a few points, a road crosses the stream and you have legal access rights.
No questions online yet. Any other in the room?
There's a potential for us to become automated.
Oh, yeah.
You would just throw something in the river or in the stream and then it float out and collect it anyway.
Yeah, so this flow path sampling approach is not unique to our study group necessarily. So there are other labs that are collecting this sort of data, and some of them have included kind of this buoyant orb that houses sensors that you kind of place in the stream and let it float down. Also, people have used like little boat drones, and so they're like these remote controlled things. And two issues with that. Unique to these headwater agricultural streams, which Ryan's paper addresses, is that with this floating orb, you're not able to cross log jams, which is something we often had to do. And with the remote controlled boat, you have to retain line of sight, which you can't do without trespassing on these agricultural lands. So for these systems particularly, this kind of manned watercraft is kind of the most appropriate way to collect the data. So thank you.
Time for one more question? No? Nobody online? All right, well, let's thank Kade one more time.
Thank you.
And yeah, I guess thank you guys for joining, and thank you all for joining online. And then that's the part where we hope Kade was sick for a little while.